can go now to the case study, and then I will give the floor to Sabine Frey.
Hello, everybody. As Christoph already said, I will show you the case study, which shows a fictive product, which will be the crash-resistant varnish for pocket flooring containing nanosilicium dioxide, and we used for our for the precautionary matrix, out of the value chain, the consumption and use for this product. First, we will need to collect information about our product. That would be the general information, which is product name. Here it's nano anti-scratch. The product contains amorphous silicium dioxide with primary particles in the size from 10 to 20 nanometers. And as I already said, our value chain processes, which we will be evaluating with the precautionary matrix, will be the varnishing the floor with the nano anti-scratch and a consumer living in a room with a varnished floor. The information for the process A, which is varnishing the floor with nano anti-scratch, would be that the varnish is an aqueous formulation. The product contains 5% of amorphous nanosilicium dioxide, and the required amount of a varnish would be 5 kilograms per 10 square meters, and the worker can treat 50 square meters per day. The information on our amorphous silicium dioxide we already have would be the particle size, which is 10 to 20 nanometer. Then the particles have no coating and no surface treatment. And the potential effect of the amorphous nanosilicium dioxide, which we get out of the literature, this information, is that its redox activity is low. The reactive oxygen species induction is also low, and the induction of the pro-inflammatory cytokines medium. And about the stability in the which is the half-life in the body and the environment, we do not know. So with this information, we can fill in the precautionary matrix, and I will show you how. First, you will have to fill in the general information. We have here who is filling in this precautionary matrix. In our case, it's the Wooden Floor Company with the contact person John Rain. Then we will give a brief description of the considered nanospecific field, which is varnishing the floor with the product nano anti-scratch by professional worker, and a brief description of the considered process step, which means in our example that it's required 25 sorry. The amount of amorphous silicium dioxide nanoparticles in this varnish would be 1.25 kilogram. And we will dispose our waste in specialized facilities. Our precautionary matrix will be filled in for the employees, and we also did a disposal step for the waste. As we already know, our nanomaterials are not coated and not functionalized. Then we will have to fill in the relevance. If our nanomaterials fall under the EU definition for nanomaterials, that's true for our nanomaterial. And we do about the primary particles for agglomerates, we said no, because we do not know the status of the agglomeration of our nanomaterials. Therefore, we take the worst case assumption, which is no agglomeration. Then the uncertainties, where we have the information about the life cycle. We have partly enough information for about our origin of nanomaterials, and we have also partly information to fill in the precautionary matrix. We know the subsequent users of our nanomaterials. and we have accurately information about the material system. Then the potential effects. This information we got out of the literature research. We have redox activity of our nanomaterial, which is low. The catalytic activity of our nanomaterial is also low. The oxygen radical formation is also low. The induction of potential for inflammatory reaction, there we have medium. And as I already said, we do not know the stability in the human body, and we do also not know the stability of the environmental conditions. Our exposition, potential exposure, the carrier material would be in this application the liquid media. Then the maximum possible exposure of humans with nanomaterials with a worker which handles per day is over 12 milligram, because we have this 1.25 kilogram of nanomaterials. Then also the worst case assumption of a worker comes into contact with the nanomaterials also over this 120. And the frequency in which a worker handles the nanomaterials in our case would be monthly. Then the maximum possible input into the environment, that would be for us up to 5 kilogram, because we will collect all the waste at the building site and dispose in a specialized facility. And the amount of disposed nanomaterial per year will be over 500 kilogram, because we do not know how the wood will be treated during the deconstruction of the floors. With this, we get to our evaluation. And as you already can see, we are on this table. We are over 20 in all the fields, which means we need, we have some tasks to do. And on this table or screen, graph, sorry, you can see the unknown fractions which are in red. And maybe if we get more information about these unknown fractions, we could lower our precautionary needs to the green box, which would mean that we are in the safe way of this 20. And as I can show you that if we get more information, maybe on the stability of our product, and we get to know that it stays 2 weeks in the human bodies and also for the environment, we will get in the evaluation a lesser unknown fraction for both, for the environment and the workers, but still not enough to be in the green box that we can say it's safe for without any precautionary needs. And then I will show you our conclusions. The first conclusion for this, the preliminary conclusion for this process would be that unknowns could be responsible for the precautionary needs for employees, and that we did second data gathering round, risk assessment, or personal protection of employees necessary. So we did that. We found new information about the stability. Then regarding environmental safety, additional data will not reduce the precautionary needs in all cases. So we will need to collect waste and make sure that it is disposed of. Then it's disposed of in a safe manner or conduct risk assessment for the environment. So after we did literature research, we know about the stability. There we have the final conclusion for our process varnishing the floor with nano anti-scratch. So we know that unknowns are only partly responsible for the precaution need for employees, and there's still risk assessment or personal protection for the employees needed. And regarding the environment, safety additional data will not reduce the precautionary needs in all cases. So we still have to collect wastes and make sure that it is disposed of in a safe manner and conduct risk assessment for the environment. So that would have been the part for the workers. Now we have the second case study where we use the precautionary matrix for the consumers. The information for this process would be that the varnish forms a solid coating on the floor. The room size would be 50 square meter and the amorphous nanosilicium dioxide content in the floor coating of the room would be 1.25 kilogram. Therefore, we will have to go back. The information we will have to fill in would be the same as for the worker assessment, that the company and also the contact person is the same. The brief description is the same of the considered nanospecific field and also the considered step. We changed here the chose scenario. Now we are using the precautionary matrix for consumers, and it also didn't change. Our nanomaterials are not coated or functionalized. Also for the nano-relevance, still our nanomaterials falls under the EU definition for nanomaterials, so it's true. And as we still do not know how primary particles are agglomerating or not, we're still taking the worst case assumption and checking here no. For the uncertainties, didn't change that we have only partly information about the nanomaterials and also partly sufficient information to complete the precautionary matrix. What changed us is here the subsequent users. We do not know them, and that's because it's not known what will happen with the varnished floor after its deconstruction. And what also did not change, we have accurately information about the material system. Then the effects, they still didn't change. We have the information out of the literature research with low redox activity, catalytic activity, and oxygen radical formation potential, with the medium induction of potential for inflammatory reaction. And here in the stability of the half-life in the body or in the human body or in the environment, we do not know. For the potential exposure, the carrier material in this case would be a solid matrix, stable under relevant process conditions or conditions of use. So the nanomaterial is not mobile. The maximum possible exposure of humans, which a consumer handles daily, would in this case be also over 12 milligram. And the frequency which a consumer uses the utility product would here be daily. And the amount of nanomaterials in utility products per year, which could possibly be input into the environment, is not known because we do not know how the waste will be treated after the deconstruction of the floor. So we get to our evaluation for this precautionary matrix. We have no need for the consumers, but there's a need for the environment. As you can see, the unknown fraction is also here very high. So we can also, in this case, go back and fill in our knowing we already have about days and weeks of the stability of the nanomaterials. And we still, evaluation. And we still can see that even if we have better knowing about the stability, we still get not into the green box. So there's still a precautionary need needed. So the final conclusion for the process consumer living in a room with a varnished floor, there, as you could have seen, there is no need for precautionary measures to protect the consumers, but there is a need for precautionary measure regarding environmental safety, especially for waste disposal. and that not reduce the precaution needs in all cases. As you could have seen, I added the better knowing about the stability, and we still need to collect waste and make sure that it is disposed of in a safe manner or conduct risk assessment for the environment.